Self-selection, date, selection, timeline. I think that's sign my license. Goodbye. How many times? That's it. Oh, let's go handshake.
Again, my name is Linda Nguyen. I'm a first year business economics major at UCLA. And today I'll be talking about how I actually landed on this major. This is an interesting one because
Okay. Ah!
Was small. We
Alright, we did this one. What else? Oh, eso. Let's see, where is eso?
The argument extends to the Acrobat menu also. Two large groups can be seen in the Acrobat design, in the first and the second tab. The constituent commands of these groups have the strongest mutual associations. In addition, the association scores of these commands represent the only case of associations being relatively large for that data instance. Hence, the two-fold objective formulation is strongly driven by the relative association values. If we had set the lambda values in subsection 4.1 differently, that formulation would not have valued the association score so highly. The two-fold objective formulation is quite sensitive to the lambda values. Further trials with the optimizer showed that multiple, quite different feasible solutions could be found within a narrow range of objective values. However, the specific relative weightage of the two primary terms in the objective function led to a situation in which an odd/unexpected placement was linked with a slightly higher objective value. We conclude that the twofold objective nature of the minimal representative formulation approach, with weighted performance from Fitts law and mutual association of commands, led to a more opaque objective function. Subjectively, it is difficult to justify the
not able to be seen through, not transparent. What did he say? We conclude that the twofold objective nature of the minimal representative formulation approach with a weighted performance from Fitts law and mutual association of commands led to a more opaque objective function. Blur. Opaque. 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 What is opaque? Opaque is can light goes through it, or is it just completely blocking? Is opaque the opposite of transparent, or so transparent is something that you can see through it like a window, and translucent is something that just passes the light but you cannot see through it. Like what? Like this is translucent. I think this is translucent. How much light passes through the, and how clearly. Definition: transparent light to pass through completely, so like a window. Clear glass, clean water. Translucent allows some light to pass through, but it scatters. Blurry shapes or colors. Opaque definition does not allow any light to pass through at all. Wood, metal. semi-transparent, very similar to translucent, but sometimes used when a material allows more light through than a typical translucent. Tinted glasses, sheer fabric, hazy, significant diffusion, causing foggy or cloudy. Turbid, luminous, bonus. Luminous is a bonus. Okay, Bianca. Oh, okay. Luminous is something that emits light rather than passing it through. Shining. Alright, so why did you say opaque objective function? What does that mean? We conclude that the twofold objective nature of the minimal representative formulation approach with weighted performance from this law and mutual association of commands led to a more opaque objective function. Does that make sense? Larry, not clear. Subjectively, it is difficult to justify the placement of a specific command in the location suggested by the optimal. Subjectively, it is difficult to justify the placement of a specific command in location suggested by optimal solution. What do you mean? When if it is the optimal solution?
Placement of a specific command in the location suggested by the optimal solution.
Subjective.
Some observations can be made nonetheless. For example, the
he's
lead
talking
elements.
about insights. Like he's saying, we solved the optimal integer MIP. Now, is there any insight we can say? It seems not.
Of most groups in the Adobe Acrobat menu are quite esoteric and unrepresentative. We note also that the twofold objective approach did not, without further information, address preferential placement of commands on desirable tabs. For example, the last /rightmost tab in the Firefox menu contains the cut, copy, and paste commands and not the help and about commands commonly expected here.
What was that? We don't know.
6.4 The IFT-based approach to optimized menu designs.
We note also that the twofold objective is a twofold objective approach did not, without further information, address preferential placement of commands on desirable tabs. For example, the last rightmost tab in Firefox menu contains the cut, copy, and paste commands and not the help and about commands commonly expected here. The IFT based, what's that? IFT, who uses help and about? I never used Firefox. So the IFT based approach to optimize menu design. Information foraging theory based to optimize menu design. Next, we consider the results obtained within the information foraging approach. The layout generated are depicted below in figure 567. The IFT based approach for a menu optimization for the Windows notepad. Oh, tab 1, tab 2, tab 3, tab 4, tab 5, and then we have, this is a menu optimized for the Mozilla Firefox browser via IFT based approach. And then they just show that the result of the optimization. Who can check what is, like for example, for Adobe, they are saying tab 1, save as other, open, close, exit, print, send file, property. But what are the names of the tabs? Cut, copy, paste, copy file to clipboard, undo, redo, delete, select all, delete all. Tab 3, find advanced search, fill and sign, done.
A few subjective observations can be made about the results. Firstly, the results for Notepad and also for Adobe Acrobat show a larger number of tabs. However, the tabs appear more balanced than with the previous method. In particular, there is less deviation among the tabs in the number of commands. An exception is the first tab in the Firefox menu, which is large relative to the others, but the remainder of the menu is well balanced. Also, the groups appear reasonable in light of usage frequency, example undo, cut, and copy, associations between commands, example undo and redo, and expectations for command position, example about. In addition, groups first items, lead items, are generally more indicative of the rest of the group here than with the two-fold approach, example full screen mode in figure 4. Finally, there is good control of loaners and also of preferential placement of elements on tabs, thanks to these being explicitly addressed in the formulation. With the next section, we explore whether these observations correlate with empirical results for user performance. We should note that the IFT-based approach also turned out to be less sensitive than the two-fold one. There are relatively few different feasible solutions in close proximity to the optimal one. The IFT approach is affected less by minor variations in the relative weights of the terms in the objective function. This should be advantageous in cases wherein the weights cannot be deduced a priori. 7. Empirical evaluation. A controlled laboratory study was carried out in line with established practices in research on menu interaction. 4. We compare average selection times between optimized and non-optimized designs when everything else is kept equal. In the conditions used, the name of a command, the target, is shown on the display and the user is to find and select it as swiftly as possible. 3. Optimized designs, the task instances described above, were compared with commercially deployed designs, baselines. A non-uniform Zipfian distribution of command selection frequency was used, as in earlier research 44. We applied the same distributions used in the task instances, which were obtained via data from the external designers, see above. To avoid interference effects, each user experienced either the optimized or the non-optimized version of a menu, not both. 7.1 Method. Participants. 24 participants were recruited by means of email advertisements and personal networks. Their average age was 29.71, SD, 3.14. 8 of the participants were female. 1 subject was left-handed. All were non-native English speakers and familiar with computers, mouse and menu systems.
Describe your
At the end of the experimental study, we asked each participant whether he or she had seen these menus before or not, whereupon about 80% claimed to be familiar with these menus but not to have any idea of whether the locations of the commands had been changed. All were compensated with a movie ticket. Experiment design. 3 applications were studied, as explained in the description of task instances above: Notepad, Adobe Reader, and Mozilla Firefox. Each user used an application either in the optimized or in the baseline condition, again, not in both. This yielded 8 unique combinations: baseline or optimized for Notepad multiplied by baseline or optimized for Adobe Reader multiplied by baseline or optimized for Mozilla Firefox. 222 equals 8. Participants were assigned to conditions by rotation. Task and procedure. The study started with a brief introduction to the purpose of the study and the tasks to be performed. Demographic data was collected with regard to gender, age, native language, and level of familiarity with menus, via a questionnaire. After this came the main part of the experiment: the label of every target command, to be searched for, was displayed at the outset, after which the menu was shown once the participant had pressed a start button. The task now was to find and click the target command as quickly as possible. Selection time was measured as the duration between pressing the start button and clicking the command within the menu. For Notepad, Mozilla Firefox, and Adobe Reader, this sequence of steps was completed 40, 80, and 80 times, respectively. The participants explored one layout at a time before proceeding to the next application. They had to find several commands within the given candidate layout, and then the next candidate layout was used. The complete procedure took approximately 30 minutes per user. Materials, for the 40, 80, and 80 commands, again, presented for Notepad, Mozilla Firefox, and Adobe Reader, respectively. The baseline designs were obtained from the latest Microsoft Windows version of the application at the time of the experiment, in January 2018. We used the roulette wheel method 45 to sample from the frequency distribution of commands in the menu. See the description of the task instances. Because the optimizer does not choose tab labels, we used the first command on each tab as the label for that tab. For fair comparison, this was done in both conditions. 7.2 The apparatus and setup. The experimental software was implemented in Python with the tkinter module for the menu system. Tkinter was used for presenting the menus and for recording selection times, mouse trajectories, and
the experimental software was implemented in Python with the tkinter module for menu system. Tkinter was used. What is that? Experimental software. So it's talking about how they run these experiments. That's all about it.
Background data. The experiment was carried out on a computer running Windows 7, with 8 GB of RAM and a 20-inch LCD display. A mouse was used as the pointing device. The transfer function and other settings of the input device were specified by the experimenter and kept constant across all participants. 7.3 Results. 27 out of the 960 trials with Notepad, 27 out of the 1,920 with Mozilla Firefox, and 42 out of the 1,920 with Acrobat Reader were removed from the final data set, for two main reasons: I, selection of the wrong command, slip, and 2, taking excessively long to find the target. We found that selection times, STS, were not normally distributed, as is common in reaction and choice reaction studies, and we used Mann Whitney U testing 46 for the statistical tests. Average ST was 1.99 s, SD, 1.12, for the optimized Notepad and 2.38 s, SD, 1.58, for the baseline Notepad design, 3.01 s, SD, 2.64, for the optimized.
We talk about like carousel presentation. But if this kind of research is already done, I don't know if there is much value to coming up with a setup like an integer program. I mean, even their work, it was obvious you should do a integer programming. I don't think that was the novelty. Maybe the novelty is just the insights, or I don't know, they say how human interacted with this computer thing. I don't know what is the novelty here.
And 3.36 s, SD, 2.74, for the baseline Firefox design, and 3.37 s, SD, 2.63, for the optimized, and 4.59 s, SD, 4.14, for the baseline Acrobat Reader design. Moreover, the p-value for all three applications was less than 0.05, showing that there is a statistically significant difference between the optimized and baseline STS.
Oh, that's interesting.
In other words, our method was able to decrease STS for these menus. We also examined the number of tabs selected before finding of each command. The average was 1.43 tabs, SD, 1.15, for optimized Notepad, and 1.64, SD, 1.29, for baseline Notepad. The corresponding figures for Firefox were 1.84 SD, 2.18 for the optimized, and 2.07 SD, 2.25 for the commercial design, and those for Adobe Reader were 2.22 SD, 2.10 for the optimized, and 2.68 SD, 2.72 for the baseline design. Statistical testing yielded a significant difference in favor of the optimized design in the case of Notepad and of Firefox. The effect was not significant for Adobe Reader. Nevertheless, the average ST for the optimized Adobe Reader was 1.22s less than the baseline value.
That's the thing. I say there are some people who do experimental research, and there should be some other people who come up, hopefully, maybe, or they are not needed. They come up with a theory that describes, or out of this data brings us something, some general approach, solution to deal with this kind. But it already has the optimization solution. So I don't know what is. Alright, just fuck that.
Table 2. Statistical results for Notepad, Mozilla Firefox, and Adobe Reader. Application: Notepad, Mozilla Firefox, Adobe Reader. Dependent variable: selection, time number of tabs selected, selection, time number of tabs selected, selection, time number of tabs selected.
So this is table, statistical results for Notepad application, dependent variable, selection time. Okay, different apps, Notepad, Mozilla Firefox, and Adobe Reader. Then selection time, and we have dependent variables or selection time and number of tabs selected. And then they compare it optimized versus baseline, and statistical values. Average for baseline is more in selection time. So optimized version is reducing the time. It's good. And what about number of tabs selected? Again, on the optimized it is less. Is it good to have less number of tabs selected? What is number of tabs selected? Does it mean they finally found what they want, or? I don't know.
The change in selection performance over time is depicted in figures
They
A.
also have a personalization.
All trend lines in these figures are default second-order polynomial functions. They consistently show a decrease in average selection time for both the baseline and the optimized menu. The optimized one showed better performance at the end of the experiment, and in some cases also initially. To understand learning effect more closely, we report average selection time per command in Figure 9. With increasing repetitions per command, the optimized and baseline menus exhibit similar drop in performance. However, the optimized menu shows a more stable trend and an overall lower ST. 8. Personalization and adaptation. The approach is not limited to one-shot computational design. In this section, we discuss two further applications in personalization and adaptation of a menu system. 8.1 Personalization. In personalization, a menu layout is custom designed for an individual or a group of users with shared characteristics. Some software allows manually customizing menus. For example, the Eclipse software system arranges its commands and menus in one way, perspective, for a developer, and in a very different way for tester. Our approach makes it possible to do personalization automatically when user data is available. We illustrate this point using the Notepad application. A novice and casual user of Notepad would presumably use the common elementary features such as open, save, cut,
What is the
copy,
difference of
paste.
novice and naive? Naive, meaning lacking experience, wisdom, or judgment. stress. Oh, okay. Novice meaning someone who is new or inexperienced in a field or task. Yeah, like naive sounds more general. Yeah, novice is about a skill, right?
And may also need help often. On the contrary, an expert would possibly know keyboard shortcuts for most common commands, due to extensive experience and familiarity. So, we expect that experts would rather only need to use the menu bar to pick rarely used advanced commands such as word wrap and font. This observation leads to two entirely different usage patterns for the two sets of users. This manifests as two different sets of frequency values for usage of commands. Figure 10 shows the menu layouts recommended for a novice and an expert.
Alright, so average selection time. Baseline is orange and optimized version is blue. And trend line, they also designed that. You can see that the optimized is better. Selection time, selection time, selection time. Okay, and then for personalization, when you adapt it for novice user profile and classic, expert. Oh, this is alright. So for new open save as page setup, print. So for novice we have added and time, date, and then exit. And for an expert we have completely different thing. Where is find? Oh, new. Where is new? Oh, new is open. Alright.
.2 Adaptation. We can also support gradual adaptation of menus. Given a menu and user data, we propose local changes to it in order to improve usability and simultaneously make it learnable. Consider that a specific user is very well acquainted with the menu layout of an application. If we propose a new layout that is drastically different from the existing one, the user will require substantial effort in unlearning the previous layout and learning a new one. To minimize this retraining effort and still provide a better layout, we propose an adaptation method building on the IFT-based optimizer. Consider that we quantify the logical difference between two different menu layouts that involve the same commands. We propose this logical difference as the weighted sum of the tab position change and the row number change of every command. Further, we constrain our computational menu design procedure to search within a specified vicinity of the previous layout. The resulting formulation is based on the following decision variables. 2 equals change in tab position for command I from original layout to new layout. E equals change in row position for command I from original layout to new layout. In conjunction with 2 and E, we also use decision variables from sections 4 and 5. Then we compute the changes in the menu layout by using constraints such as E equals R, R6N, E equals R plus R6N, A. 9, here R is the row position of command I in the original layout. The objective to appreciate the impact of this gradual adaptation of menu layouts, consider figure 12. This shows the gradual adaptation of the menu layout where we balance the proximity to the original layout against the objective of getting better performance. In this figure, we intend to demonstrate that our approach supports controlling the amount of change made for adaptation of a menu layout. We vary the proximity of an adapted layout to the original layout, x-axis, and see what performance improvement we can achieve with this proximity constraint, y-axis. The blue line shows the improvement in performance value, Fitts law. The green line shows the loss of familiarity, change from original. The results reported here are for the Notepad menu. 9. Discussion and conclusions. This paper has contributed to the study of algorithmic methods for computational design of menus. The design of menu systems strongly impacts the usability and learnability of the computing application. However, currently menu design remains a manual. Tab 1. New Tab 2 Undo. OpenCut. Tab 3 Word Wrap Font. Tab 4 Status Bar. Save as Copy Paste. Page Setup Delete Print Find. Exit Find Next Replace Go to select all time date. A. Default menu layout for Notepad application. Tab 3 Word Wrap. Font. Tab 4. Tab 1 Tab 2 New Undo OpenCut Save Copy Save as Pastor Page Setup Delete Print Find Time Date Find Next Exit. Tab 5 View Help About Notepad. Status Bar View Help. Activity Almost exclusively, there is no well-established or commonly accepted computational technique to automatically generate or refine menus. The absence of an effective mathematical model for a menu hierarchy such as the Minimal Representative Formulation, MRF, proposed here, has made it difficult to test for reliable objectives and to distinguish a good solution from a poor one. To the best of our knowledge, no earlier approach provides guarantees regarding the solution quality, yields a hierarchically organized menu suitable for large command sets, is not overdetermined by previous designs, example on account of a data-driven approach to the objective function, does not require much input, relative to the frequency of each command and pairwise association scores, can be used for one-shot design as well as adaptation, and is computationally efficient for large menus. Our contribution through the MRF is to enable a compact. The MRF approach provides enough. Our contribution through the MRF is to enable a compact, flexible, and purely linear IP formulation for solving the assignment and set covering problems simultaneously and within reasonable computation effort, thereby warranting application in regular menu designs. The MRF approach provides enough flexibility in defining the objective function to cover the wide variety of factors involved in menu design, the total number of tabs, the length of individual tabs, the number of groups on a tab, the length of individual groups, intra-group and intra-tab associativity, frequency of usage of the commands, etc. The MRF supports diverse evaluative functions. This is valuable for researchers because various hypotheses can be tested with relative ease. Specifically, evaluation functions can be expressed that refer not only to the position of any item, like in the assignment-based approach, but also to its membership of a set such as a tab. We implemented a classical objective from the previous literature and showed that solutions for the resulting mixed integer programs can be found within reasonable computational effort. The results yielded by the two-fold objective approach, while not entirely unreasonable or impractical, suffer from a few shortcomings, such as non-intuitive placement of commands. Our novel information foraging-based approach addresses these problems. It addresses users' decisions in zooming in versus skipping menus when searching for a target. The layouts resulting from the IFT-based, information forage theory, approach appear to be more balanced, better organized, especially lead items, and aligned more closely with expectations regarding command placement. Although the original form of IFT involves nonlinear models of user behavior, we have demonstrated that a simpler, purely linear, MIP-based, mixed integer programming approach yields good results within reasonable computational effort. Empirical evaluations suggest that computationally produced menus can be on par with commercial designs as long as the input data, here, frequencies of selection, reflects actual usage. However, our empirical evaluation assumed that the usage frequencies match those used to run the optimizer. Future work should explore how sensitive the outcomes are to a mismatch between inputs and actual use. Moreover, the problem of how to computationally produce labels for formed groups and tabs remains an open problem. We draw two conclusions from this paper. The immediate conclusion is that IFT can be used as an evaluative function in computational menu design with good results. In conjunction with the MRF, this offers a rigorous, coherent yet flexible new framework for computational menu design. Our decision variables and the resulting constraints work with standard commercial MIP solvers and do not require any specialized contributions. For example, we do not require any specialized decompositions, relaxations, or column generation techniques, which are often used to enhance MIP performance. This opens possibilities for utilizing more complex evaluation functions with relatively lesser effort. In future, to make the method available for interactive design tools, we will explore heuristic variants and relaxations of the IFT-based approach, which may allow interactive level performance with large task instances. Another limitation to be overcome is related to the nature of the task instances. Even if filling in an association matrix constitutes only about an hour's work for a reasonably large menu system, it may not be practical for some use cases, for instance, in agile or rapid development cycles. We will explore word embeddings and other machine learning approaches that can automatically discover command pair associations from data. Moreover, the scope of design decisions covered needs more attention. Further work should examine other decisions in menu design, such as label selection and shortcut assignment, and expand from tabbed/group menus to other types. In our opinion, the general class of exact numerical optimization techniques holds promise for hierarchically organized user interfaces more generally. More research is needed to build on this finding. Many user interfaces are organized as trees or graphs navigated by selecting from proximally available options 13. The MRF offers a natural representation for the key decisions, such as which item to assign to which display, in which group. Deepening hierarchies can be addressed by recursively adding decisions. We found also that the sample, discard, explore formulation of IFT captures an essential aspect of a navigating user's decision-making. This is an improvement over previous work in user interface optimization, which has utilized mainly non-hierarchical evaluation functions 21. The linear reformulation proposed here is also sufficiently efficient and avoids resorting to meta-heuristic techniques. However, more work is needed to address the different modalities of menu access, such as shortcuts and context menus, which add redundancy to the optimization problem and require users to learn more complex strategies of menu use. Moreover, the naming of tabs remains an open problem. While word embeddings produce good results for pairwise association scores, finding a descriptive label for a tab may require considering other types of semantics, such as part-whole relationships. The code presented in this paper is made available via our project page. References: 1G Bailey, E. Lecolinet, L. Niga, Visual Menu Techniques, ACM Computing Surveys.
Okay, let's play some. light is bad. Okay, I see it. What the fuck is that? Dude, a window does so much light. You don't understand me, to be honest. Ah! Dude! Alright, I need to fucking... Fucking with that gun. Face. Oh. Red dose, dead rose. Fuck me! They come back from this side, this is one time. Let's do it again. Oh, what were you doing, guys? Poseidon. Oh, fuck, dude. Can you fucking hold both our ground? Wow, they look far better. Bunch of novice teammates. Javier. Javier. Dude, Javier. Javier. Where is he? Fuck! fuck? I didn't? Dude, don't go ahead. Don't go forward. Just stay here. You don't need to go ahead. Just hold it here. Ah, dude! Oh, motherfucker. This fucking asshole. He's just hiding the thing. I did a good job. I did a good job. I did a good job. He will just slaughter us here. It's 9 a.m. What was that? Why are you doing that? Hardy. Fucking guys, stop! Don't go ahead. How is that possible? They're killing 4 of us. How many of them? Dude, how many are they? Let's go baggage, guys, you fucking assholes. Don't move! Oh, what was that? H was the one that... What is the shortcut key for talking in Counter-Strike?
In Counter-Strike, the default shortcut key for using voice chat is usually the K key. When you hold it down, you can talk to your teammates in-game. You can always customize it in the settings if you want to change it to something else.
Motherfuckers, stay here. Okay, I don't think you do.
Alright, if you need any more...
How can I write? Communication matters. All of us are here, fuckers. How? What are his guns, by the way? Guys, don't move. Just don't move, can we? How can I talk to this? Don't move! How many of them? Guys, how can I write? Don't. Alright, what was that? Okay. Dude, they're so good. How do you write? Why write? Dude, they're so fucking good. Who shot? Dude, I killed him. Fucking! that motherfucker over there. How many of them? Jesus, we are everywhere. Did I got that? Actually, I was top 3. One baggage, one baggage. Woohoo! Dude, come on. He's covering back. Dude, I should move. got them. We got them. We got them. See? Dude, I'm really good. I think actually a lot of people left, but... Last time. Stay in the base. Don't go anywhere. As soon as we got him. I fuck. Damn, we killed all of us. They're so arrogant. They have everything and they were just standing there. Wow. Alright, that was good. Oh,